Okay. With any luck, you guys can hear me out there. Am I on the right meeting? There's no one here. That makes me very suspicious I joined the wrong one. Okay, now there's people here. Okay, good. All right. I guess it wouldn't let them join. Have you guys tried joining the WebEx live? Does it let you join before I arrive? Okay, so it tells you you gotta, okay, all right. Yeah, so everybody's bailing in now. That's why. Okay, let me see here. Where is my WebEx window? Here we go. Share content. So I'll repeat for the recording and for you guys what I said. The exams are not geared to be really tough. I've kind of changed my approach on exams over the years, and I put more focus on the homework. But what we're going to do today is homework number 4 together. You'll find it on the class folder, and turn it in by, the end of the day today. Like, let's set a time here right now that I'll release the solutions for it. And as long as you have your homework in before then, it won't get counted late. But the TA, I'll basically tell them, if you turn it in and you have something down, I trust you guys to have spent the time to understand the answer. I don't expect you to recreate everything that we're about to do. You can take a shortcut and say, here's one of the times when the threshold changes, etc. I'm like, good, okay, so you're telling me you get it. You're telling me you know how to do one of the times. That one looks right. I believe that you could do the next 5, but let's not waste the time doing it. We'll do it together in class. So I'll tell them to go easy that way. But if you will find answers out there to the problems. So if you just worry about copying them down and getting them turned in, you'll probably get exactly the same grade as somebody who sits here today and does it the way I just described, but you will not be prepared for the exam. Right? Turning in 100 on that is not a guarantee. So I'd rather you stop me and make sure we understand the concepts as we go along, and you get a chance to learn something cool about networking. I could turn the lights off on this, but I think they're over here. Didn't we decide that? So what time do you want it to be due tonight? Here we go. We can make it like 6 p.m. or 7 p.m. or 8 p.m., something like that. Until it's due, I won't release the solutions for you to study from for this homework. 1 and 2 are out. I'll put 3 out this afternoon, and then the question is then on number 4. So what do you think? You guys late night night owls or early birds? Night owls. So you want a little more time to turn it in, like 10, midnight? I mean, it's up to you all. When do you want to see the solutions to study for this homework? We can do 8. Anybody else got a different idea? 10? All right. Does that work? I hear more 10s than 8s. Is that all right? You okay with that? You're a little tired? Text me at 8. Okay, send me a text. I'll send you the stuff. You just can't put it on the group deal. That's all. Okay. I'll bend over backwards to help you guys. I'm with you. 10. I'll have to stay up. Yeah, but I get where you're coming from. Okay. So I want to ask you guys some questions, and these will be easy to answer probably only if you spend some time with the recordings, but we're going to try to go over them together. So there's 2 transport technologies that we've talked about, TCP and UDP. The recordings talk about them in a lot more detail. So what I want to ask you is which of them, if either, maybe it's both, exhibit each of these characteristics. So the first one is breaks oversized messages from the application coming from above into reasonably sized segments that can be sent out over the network. Which of the 2 transport technologies do you think would need to be able to do that, would have to do that? TCP, I hear. And what about UDP? Okay, so what if it's too big for the network? So sometimes applications will send 20, 30,000 byte messages, however long the variable will let it in that implementation on that operating system, and you may be running on a network that can't handle packets nearly that large. So TCP isn't required, UDP isn't required to size things for 4 layers down. Remember I told you you're only supposed to have to deal with the layer above you and below you. But if you know that the plane only has an opening in the side, on the side this big, why would you send big giant luggage? Why would you take it even at the ticket counter? Somebody's just going to have to open it up and repackage it into much smaller cases. So that goes on with every packet. And it's something that you have to do for both TCP and UDP, because you get to pick which transport layer. You could send the same amount of data over either one. So when you write your code and you put data in a variable and you pass that to the sockets library, it's up to you how much you're passing, and it's up to the operating system's implementation for how much rope they're willing to give you. Do they only give you room for 1,000 bytes, or do they give you room for 100,000 bytes? That's not specified in the standard. You get to code that if you're the one writing TCP or UDP. So it's actually something that both sides have to do. Does that make sense? All right, what about provides a checksum? Has anybody run into checksums on the recordings yet? So we'll talk about them a little bit today. We'll do a couple together, but a checksum is a quick math sort of remainder calculation, is one way to look at it, that you can do it by turning whatever the packet is, treating it like a bunch of integers. And after all, it's all ones and zeros. We can interpret any string of ones and zeros as integers if we want to. Even if I tell you, here's the complete works of Shakespeare on a drive, you look inside the file, and at some level, it's all ones and zeros. But if I tell you it's the complete works of Shakespeare, you'll probably try to interpret it byte at a time as an ASCII character. You're expecting English out of it, probably, not integers, like 625, 3206. Why would he write that? That doesn't even rhyme. But you can treat ones and zeros as integers. So what transport layer technologies and lots of others will do, as the packet is coming in, one of the things they're doing is keeping a running total of a sum by breaking it up into 16-bit numbers as it goes along. And when the packet is over, it looks at what the sum is, and it ignores any carryout and just takes that and adds it to the end of the packet. When it arrives at the other end, you repeat the process. You should come up with the same total. And if you don't, you know that the packet was corrupted along the way. So this is done all the time to try and detect errors. So has anybody ever entered a credit card number on a website, and before you even submit it to process the transaction, they tell you the number's wrong? Yeah. Do you know why? It's the same exact thing. The last few digits of your credit card number are based on the rest. They're check digits. So they may make the last digit or two, whatever would have to be added to the rest of it to make it, say, a multiple of 10. And there's rules for credit cards that we won't go into here. Same thing with UPC codes. There's codes, that extra digits that are embedded in there. So when Walmart scans the barcode, one little error, it'll catch it. It'll know there's something wrong, and it will not conclude, I have just read the correct barcode, and therefore I will go look up the price and charge the customer that value. So you add extra digits sometimes to do these kinds of things. Telephone numbers don't do that, so you make lots of wrong phone calls all the time. But with data networking and with lots of other standards, we add checksums. They're optional, but not with TCP. With TCP, you have to have them. And in advanced networking class, I think Om probably goes into this, Om Prakash and Nawali, but they're actually quite interesting, the rules and the algorithms that people use, and it's kind of easy math, but very interesting what they've done it. Okay, which one of these two retransmits packets that are believed to be lost? It'll keep track of your packets, keep a copy of them, hold on, wait till they get an acknowledgement back. TCP. Does UDP care about much of anything? Just remember, UDP is the lazy, evil twin brother of TCP. It just doesn't care about anything. Bad attitude, doesn't want to do anything for you. You hand it something to do, it just flips it out the window, out the back. I mean, like, you've had a roommate like that at some point, haven't you? Some of your little brother or something like that, or God forbid, a big brother. So TCP is nicer about that. If you want not to have to write your own code to make sure things got to the other end, TCP will do that for you. It will help you do that. It's 40 years old. It's pretty long in the tooth, and people have written some things to kind of replace it. lately, but it's the dominant protocol used on the internet to send things where we don't want errors to be introduced. So files, movies, images, documents, but there are things where we don't care about them. Streaming audio and video, for example. Okay, which of these two do you think, and there's only one answer for this one, which of these two adds much less delay from the time you hand it data to the time it hands it down to the next layer to get it going towards the network? UDP, right? Flips it out the window. Good. Correct. Okay. Which one is careful to not congest the network? Yeah, TCP. UDP could do that, but UDP doesn't care. Remember, it's like couldn't care less. Asks permission before sending. Yeah, that's a good guess, right? Ask permission before sending. UDP, it's like, ready or not, here I come, right? Oh, do you have enough bandwidth? Don't care, here it is. So for that reason, some administrators block incoming UDP traffic, which is interesting if you're trying to build a streaming service, and that's the protocol that you chose to use. What are you going to do if you can't get your packets in the door? Okay, and then which of these two run at layer 4 of the 5-layer stack in the transport layer? Both. These are transport layer technologies. Good. Trick question. I love trick questions. So like what color life force? So I had a chemistry professor in high school that I loved and hated. You know the type? Really smart, learn a lot, but is so much smarter than everybody else that when he plays a joke on you, you know, you fall for it and then kick yourself. So you guys may have seen this, and he didn't invent it either, but he came up with this molecule on the final exam in, I think, 11th or 12th grade. I can't remember here. There's supposed to be 8 of them. I don't know if there are. And he goes, okay, what's this molecule called? So first of all, you know the Fe is the iron atom, right? All right, so what's this molecule? Ferris wheel. Yeah. You know, the ride that you have at the fair when you get in there? Yeah. So he was one of those guys. So TCP retransmits things. UDP doesn't care. And so if packets get dropped by UDP, it will not even know, let alone bother to retransmit them. So I could tell you guys some UDP jokes, but half of you wouldn't get it. Get it? Okay. Get it? Half of you wouldn't get it? All right. Okay, so suppose you are writing the MLB audio stream for the Astros. And let me pull up my chat window here, make it midnight. Okay, I'll do this as late as I can. You prefer to use UDP to send your packets to your users. What are the 2 most important reasons why you would use UDP for your streaming audio instead of TCP? Faster is a key one. And why else? I mean, exactly. You don't care if packets get dropped. It doesn't harm the overall effect. They'll repeat if we get a home run, I promise. They'll tell you several times. Anybody watch the game yesterday? I guess the Blue Jays got tired of losing. We scored 22 runs in the first 2 games of the 3-game series. Yesterday, they scored 11 against us, including 2 3-run homers in the 7th, and it was like a butt kicking. So it's like, okay. So I was sending all my Toronto friends snide remarks after the first and second game, like, well, I guess the Raptors used up all of Toronto's luck, huh? There's none left for the baseball team. And then, boy, they blew up my phone yesterday. It's like, okay, I deserve it. Like, you know, let's like keep it going, keep it nice. So yeah, fast and you don't care. If some of your packets get dropped, doesn't really matter. Okay, so because UDP has no handshake or flow control or congestion management, things that keep you from overwhelming the recipient and not congesting the network, some of the things that we just asked about in that table, it's a popular vector of attack. So administrators will usually turn it off because they don't get any say before the UDP packet arrives. Unlike TCP, which asks permission, and if told no, will not send you anything, UDP doesn't care. It'll send you stuff as fast as the application asks, whether you're ready or not, whether you're even turned on or not. Couldn't care less. It can be a an IP address where there's nobody even listening on the socket at the moment. It could be just filling up the buffer, for example. So lots of administrators will turn it off. What would you do as an application author? What would be one remedy as an application author to still get your Astros audio baseball stream through to your sports-addicted computer science networking professor if he works at a place where they block incoming UDP? What would you do? I'm not going to let you get any UDP packets in. What's your other choice? TCP. So you'll find sometimes YouTube and other streaming services will send their data to you as TCP streams if they can't get them through the firewall as UDP. We're more sophisticated than that in general. Firewalls, which are devices that sit at the edge of your network and try to prevent bad traffic from coming in, they know the difference between packets that are arriving unsolicited and ones that are arriving in response to something you asked for. So if you asked for the audio stream and it's coming in as UDP, usually we will let that in. The firewall will permit that to come in because it seems as if it's coming from an address that you just sent a request to. And they're even smart enough to know it looks like it's an audio stream, so that makes sense that it would come in UDP. So those devices are more sophisticated, but the sort of brute force rule is if you can't get it there with UDP, then maybe in your application, you teach it to request a second time via TCP instead. And maybe the server can get that through instead. So the server is not going to know if your packets are getting in or not. If it's sending you UDP packets, UDP is not going to help you figure out if they're getting there or not. Remember, it doesn't do any acknowledgement. And so the application author, you have to write extra code. So if you're running a streaming program and you attempt to connect to the Astros baseball radio stream and you tell it, here's my credentials, start sending me the broadcast, and they do, they are assuming you're getting it. So what you should do as an application author is add some extra code that does your own checking. And there are packages that will do that. There are libraries that will do that for you. But the general idea is that the client will send something back saying, are you trying to send me something? I'm not getting anything. Would you try TCP? And the server will go, oh gosh, I'm sorry, I didn't know. Yeah, here we go. Let's try that. So it's harder on the server. They have to build buffers. They have to implement counters. And it slows the server down more than sending UDP. They may have to suppress retransmission. Even if they fail to get acknowledgments back, you may have to hack your code to lie your butt off about, yes, I'm getting everything, it looks fantastic, keep it coming, when half the stuff's being lost, because you do not want to have lots of retransmissions. But that's an interesting area to try to code, because any place where hackers have figured out how to swamp a site, let's look at the bad side of it. If I overwhelm you with billions of UDP packets, confident that they could all possibly reach your computer, I'm going to put you out of commission. I'm going to overwhelm you. So that's why firewalls don't want to let it in. So you're going to have to figure out how to get your traffic in when lots of other traffic is not supposed to go in. And the games, let the games begin. It's just a constant arms race against hackers. So anytime when we look at these protocols this semester, and I'll mention it a few more times, and you'll hear it all the time in the recordings as well, anytime you see something that looks like extra trouble, like why would you go through that extra step? Like even the three-way handshake. TCP has what's called a three-way handshake. Why not just a two-way handshake? Three-way, what the hell is a three-way handshake? Well, anytime you see something like that, it's extra trouble, you should assume it's because hackers screwed it for everybody else. Right? So if we're going to extra trouble in our protocols, it's because somebody else ruined it for everyone by exploiting that as an attack vector. 100% of the time, that should be your default answer. So I'm a super paranoid person, not negatively so, but I'm constantly wondering, like, have I thought of everything? Is there something that could break here? Not like they're all out to get me or something, but they are. They are absolutely all out to get you. So it might make you sort of a interesting personality to live with, but it makes you an excellent network manager. So if you are paranoid and you're wondering, like, I don't know if you know, there's a great propensity for good salespeople to have attention deficit disorder. It's a huge attribute, actually. So, but for networking management, if you're paranoid, you've got a great career in networking coming for you, right? Because if it can go wrong, it will, and it probably is going wrong right now. You just haven't detected it yet. Okay, what about the opposite problem? A developer who must use UDP, but nonetheless would like some reliability. UDP is not going to provide it, so what do? Yeah, do it yourself. We just talked about it, right? Add it to your own app. If the network infrastructure isn't going to provide the reliability you need, then do it yourself. You have to do it. Right? So there's lots of parallels. If you order a package from Amazon and it doesn't get there, tell them, they'll ship it again. They don't really know where the package is usually, although they're getting better at it. So there's parallels to that. And you got taught as a user, you're the client in this case, to tell the server, Amazon, I did not get the package. But the package delivery system did not do that on its own. You had to intervene and tell them, I never got it. Anybody ever had to do that? Yeah, you bet. Didn't get the check, can you resend it? Didn't get the credit card, et cetera. Or in my case, why am I getting all these magazines in my mailbox all of a sudden? We talked about that last time. That was a denial of service attack. Okay. The type of checksum that TCP and UDP use is called ones complement. Have you guys been exposed to ones and twos complement math before? If you did computer architecture from me, you did. But ones complement math is a way of quickly adding numbers together. And the idea behind ones complement math is basically, if I can get this to pull up here, Ferris wheel, you'll remember that. I predict you'll be using that with your kids someday. Hey, you might even use it this afternoon. The fact that I remember it 45 years later bothers me a little bit, but what can I do? So the way ones complement works is you add two numbers together, and if there's any carryout, you add it back in again. So let me give you one with a carryout. 10111100, and I think this one will have a carryout. 111. 1 plus 1 is 0. There's a carryout. Add it back in again. It's going to turn the number into that. So with ones complement, you add the numbers together. You add any carryout back to the subtotal, and stop. Your answer is going to be the same number of bits as the numbers you're adding. That's why when we had carryout and it broke that rule, we had to take it and move it back in and add it up again. But you do it one time and stop. Okay, so how does ones complement work? Let me give you a little bit more insight. This is on the videos as well. But let's say you have a packet, and we have this habit in networking of drawing packets as data structure diagrams, and sometimes we'll divide things into 3, but they're always 4 bytes wide. Just tradition, 32 bits wide. So if you have a data structure that you decide to design for TCP, and you're going to put places in this data structure for things like the port number and the type of protocol and the overall length of the packet, and one of the things that you'll put in there is a space for the checksum as well. That'll be one of the fields. And then, of course, you're going to have space for the data that you're being asked to carry by the application. And that'll be most of the packet, most of the time. But you will draw it always in every textbook as a rectangle that is 32 bits wide. So when we do ones complement, there's lots of ways of doing it, but hey, why not go with the flow here? And so what we do is we treat this as 2 16-bit numbers, one here and one here. And we, as the packet comes along, this is 16-bit number 1, this is 16-bit number 2, number 3, and number 4, and you just go on and add them all up. You're just keeping a running total like this as you go along. And there's a place in here, one of the things in here is a place for the checksum itself. Remember, the checksum actually gets added to the data. So the idea is somebody hands you a packet to go out the door, and before you hand it down to the next layer, one of the things you'll do is add a checksum field. Just a little bit of error checking, just to kind of catch the most common errors. But where are you going to put it? There has to be a spot thought of ahead of time inside your data structure. So before I fill that value into this rectangle here of 16 bits wide, what's its value to begin with? Until you put numbers into RAM and you turn your computer on, what are all the bits? Zeros. So the checksum will start off with just an empty space, but we know better. It's not really empty. We interpret that to be zeros. There's no empty. It's like either ones or zeros. That's until I was tall enough to see over the counter at Baskin Robbins, my mom used to tell me, they have chocolate and vanilla, which one do you want? And I believed her. And then when I got tall enough, I'm like, hey, really? I mean, come on. So this thing will be all zeros to begin with. So if I add this checksum to the total, when it's all zeros, when I'm calculating the checksum, will it change the total? No. So I just blast through, add this whole thing up. I finally get my subtotal down here. I do the little carry out, add it back in. I finally have my grand total here. And now it's ready. The packet is ready to go out the door. I'm ready to send it down to the next layer. The last thing I do before I hand it in a function call to the IP layer is I come in here and I overwrite this value. So now it's the original value it was plus whatever the checksum is. So I've added one more integer to the total. All right, so here's where the magic happens. So let's say my total from adding things up is this. And I calculate the checksum for it, and one of the things I didn't exactly explain, and I feel a little guilty because I'm depending on the recordings because we don't have 5 live sessions a week, which was the compromise I made with the computer science department. But you'll also do an inversion in these things as well. So I'll show you how it works. So let's suppose this is the sum that I came up with, all right? And I've already done the addition. You know, it's basically this new number here. So this is it. The last thing I'll do before I pop it up here is an inversion, which isn't exactly really one's checksum, but it's part of the rule that we'll do here. It's an inversion. So it's actually this value that I'll put in there. Why would I do that? Why would I invert my total and put it in? It's because of what happens when the packet's received at the other end. The person at the other end isn't going to want to spend a bunch of time trying to figure out if the packet was corrupted or not. So I can come up with this scheme. It certainly was easy for me as the sender to calculate it. I just kept a running total as the packet arrived, and I did the carry out bits, and I stuffed the value in the checksum. But I'm telling you I want to invert it because that is the key to make it easy also for the receiver. And here's why. What's going to happen at the receiving end when they receive the packet? They're going to reproduce exactly what I did. They're going to be receiving the bits, and in addition to interpreting them as a TCP or UDP packet, they're also going to be adding them up, keeping a running total as if it were a bunch of 16-bit integers. And what total are they going to get? Well, they should get this number plus the one I added to the packet, plus this one, right? I mean, the packet without the checksum value was all zeros, we decided earlier. So that's what gave me this. Now I've added the checksum to the packet, but I did it by inverting the total. So what I'm actually inserting in there is another integer. So what am I going to get? This is everything. This is the whole packet except the checksum. And this is the value in the checksum field. So what do I get when I add those together? What do I get? All ones. All ones. So in computer architecture, if you're writing the assembly code to make your TCP routine run quickly inside the OS, how can you quickly tell if a number is all ones? Have you guys all had 2440 computer architecture? Some of you have, some of you haven't. I think it's required, but I'm not positive of that. So if I'm looking at an instruction set in most CPUs, I don't have an instruction that says, look at all the values and tell me if they're all ones. So what would you do to conduct a test? Add 1 and see if there's overflow. I'll meet you halfway, right? Add 1 and see if the overflow flag turns on. There's only one situation where that'll happen, if it's all ones. If there's a single 0 in there anywhere, adding 1 will not overflow. So that can be done at light speed. Computers are good at doing that. They have ripple adders built into the hardware. If you add 1 to the total of these things, if the overflow flag is set, you clap your hands and go, that must have been all ones. Therefore, the sum of these things must have been perfect complements of each other. Therefore, nobody changed any bits in this, nor did they change any bits in this during transmission. When it was out on the evil network in harm's way, it made it safely to the other end. Now, checksums aren't perfect. They actually miss errors if there are multiple of them, but they're good enough to catch single errors, which is, of course, the vast majority of errors that are out there. So it's kind of interesting, but what I hope you get out of that is you need to know what's happening all the way down at the hardware layer before you design a protocol. If you do something like check all the bits and see if each of them is 1, or add 1 to them and see if it's 0, there's a command to do that as well. There's an assembly command to do that. Is the number equal to 0? That's built into every ALU. Either one of those things would work, but design it that way because it needs to run super fast. You do not want to slow things down. In fact, you cannot slow things down. You are going to need every trick in the book to make routers run fast because some of them handle hundreds of billions of bits a second, believe it or not, in the core. So you don't have time to do much of anything. Okay, so back to the problem. How would we calculate the ones complement of this? So normally we use 16-bit numbers, but we don't have that today. So this is the comedy part of the lecture because 95% of the time I screw this up. So watch me like a hawk. I could have already screwed it up by just writing the number down wrong, but seriously, I'm so over it of being embarrassed by it. It's just the way it is. I mess them up. Here's the tip I'll give you. Only add up 2 at a time. Even Microsoft and their hardware for their network cards drivers, they only add up numbers 2 at a time and they keep a running total. And then they do the carry out at the end. So here we've got, what is 1 plus 1? 2. So it's not 0. Here's a trick that you can use. 1 plus 1 is 2. How do you write 2 in binary? 1-0. So I'm going to write 1-0. I may write them in different places. That's a way to add up lots of numbers at once. So if I add up, for example, 01, 01, and 01, what's 1 plus 1 plus 1? 3. What's 3 in binary? So I better have a 1-1 someplace I'm going to add to this thing. So that's kind of the idea. Okay, so 3 ones gives me a 1. It's a 3, so I wrote down 1, 1. That's a 3. This is a 2. 2 is written down that way. 1 is written down this way. 1, 1. 1 and 1 is 2. So there's 2. I wrote down 2. And now I'm going to add the other number. 0, 1, 1, 1. 0, 1, 0, 0. And you think I got this one wrong? Yeah. Told you. The last bit is 0. Yeah, it didn't write correctly for me, so I rewrote it again from memory. All right, so let's. Thank you. Thank you for catching that. Okay, this makes it a little easier. 1 plus 1 is 2. 1 plus 1 is 2. 1, 1. 1 plus 1 is 2. Okay, do you agree with me now? All right, 0, 1, 1, 1. 0, 1, 0, 0. We'll add these up. 1, 0, 1, 1, 2, 3, 2, 2. This one is a carryout. I will add it back in. So my answer will be 0, 0, 1, 0, 1, 1, 1, 0, because I added it back in. So that's the sum of it. And we'll reverse it to create the checksum. And so that's the value that's going to go in my packet. So if this is the value, great. If I screwed it up again, you know, sorry. But that's what I think it is. Why do we take the 1's complement instead of just using the sum? So the complement part is the reversal, and we just talked about that, right? To make it easy on the receiver, to make it easy to detect the error, or fast, or short code, or to be able to do it in hardware, or something that shows you're thinking about the guy at the other end. Right? CPUs can flip bits. Those are really easy. There's commands to do that, to invert, built into the hardware. What you don't want to ever do is write code that the compiler has to stretch out as a bunch of lines of code in assembly. You want to try to write code for drivers that, as close as possible, matches exactly one of the machine language instructions, something in your instruction set architecture. How will the receiver detect errors in this scheme? Just repeat the sum. Now that the checksum is inserted in there, the answer should be all 1s. So they'll just repeat it and see if it's 1s. You don't have to tell me how, you'll see if it's 1s. Can a 1-bit error ever go undetected? So if I change 1 bit in my scheme, you can pick whether it's in the top half and the bottom half. This top part is the result of adding lots and lots of numbers together. But if you change one of the bits anywhere, it's going to change this total, correct? So if you add it, so let's say we change this one right here. Is it going to add up again to 1s? No. Is there any bit you can change where it will still add up to 1s? Not just 1 bit. But what if I corrupted something that made this total this, and by coincidence, it also changed the value in my checksum field and made that one. So it flipped 2 bits. One was a 0, one was a 1, and now they've changed positions. Can I detect that? Is that still going to add up to 1s? Yeah, it will. So there's lots of ways of fooling this. It's easy to fool it. It doesn't care where the 1s are. It's just adding up how many of them there are. Just like with regular math. If I tell you I have $100 plus 6 more, that's the same thing as telling me you had $6 and then 100. I don't care of the order. And that's the same way it is. Or if I told you it's $123 and 15, it's the same thing as $113 and 25, isn't it? Or I just took these two numbers and reversed the order. Doesn't matter. So there's lots of ways of fooling this. So for that reason, 2-bit errors can't go undetected. Okay, so calculate the 1's complement of these two sums. Let's see if we can do this. I don't remember what it was about this one. Probably it adds up to 1s already or something crazy like that. So 1, 1, 0, 1, 1, 0, 1, 0. And the other one is 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1. Okay. 1, 1, 1, 1, 1, 1. 1 and 1 is 2. 1 and 1 is 2. Add 1 to it again. What am I going to get out of this? I think it's that, isn't it? Does that seem right? Okay. Give an example where 1 bit is flipped in each of the 2 bytes in the previous problem that does not cause the 1's complement to change. So the way to go about doing that is to pick, whoops, I wanted a box. This is a good candidate because the bits are opposite values. So is this one, so is this one, and this one, and this one, and this one. That's why I created the numbers the way I did. These two, it won't work. If you change these 2 bits, 1 to 0, 0, you will not get the same total. So this one won't work. But the rest of them, all of the rest of them will. You can just trade places, top row with bottom row, or any of those blue boxes, and you'll get the same total. So it's okay. So how do you know then whether to be confident or not? So one of the things that we'll see next week, yeah, I guess it'll be next week, is anytime you design something at a lower layer that introduces higher error rates than were assumed to exist with things like the transport layer checksum, you must clean it up. So think about wireless, for example. Wireless is super prone to errors. There's all kinds of wireless interference going on all the time. So the error rate is orders of magnitude higher than it is with a wired network. But it's the same checksum. So I'm automatically suspicious that my checksum is not going to work well for me anymore because there are probably going to be tons of multiple errors. If it was not very common with cable, it's going to be a lot more common with wireless. So what's the right approach as a protocol developer to deal with that? Your approach is to put your thumb on the electrical engineer that's doing the lower layer design and make sure they add their own error correction scheme to the hardware they're building to produce output that has an error rate exactly the same as, say, Ethernet on a wired network, because that's what this was designed around. If I use Ethernet and I add to it in the transport layer this checksum, people will be happy. Errors will be very, very rare. Well, you're not going to rewrite TCP and UDP just because somebody invents Wi-Fi or another version of Wi-Fi. So it's on that layer. So when you introduce, basically think about it like this. You go to a campsite, you stay the weekend, you clean up when you leave. You make the mess, clean up after yourself. If you design a protocol at a lower layer, particularly hardware, that's very prone to errors, add your own error correction scheme to it. And that's exactly what happens. People will add their own, because we cannot rewrite the higher layers of the stack, nor are we willing to tolerate tons more errors for speed. It just won't scale, won't work that way. Okay, the book, good luck on your interview. The book shows a couple of examples. Let's see if I can get this. I'm using the wrong command to do this, is why. So the book had an example of a network that was very inefficient, and it starts to get us into the way timelines work. And I'm going to draw a new screen here for us. So basically what they said was the sender wants to send a packet to the other end, and he wants to make sure he gets an acknowledgement back that the packet was successfully received before he moves on to the next one. Okay, well that's okay for a short cable, like to your printer. Send a byte and get it back, because the time it takes to get it there is nothing. And so maybe it needs a moment to think about whether to send you the acknowledgement back or not. But once it decides to send it, transmission speeds are really fast and the cable is short. So it's not going to add any delay. So you're not going to be penalized for doing it. But what if I had to send a jigsaw puzzle to you, lots and lots of pieces, and I put a piece each in an envelope and mailed it to you across the country instead? That's a lot slower than handing it to you one by one by one, where there's no transmission, there's no propagation delay. Now there's an enormous propagation delay. How long does it take the Postal Service to deliver it? So you've got this huge postal network built. It's ready to handle lots and lots of puzzle pieces at the same time, and you're using the whole thing to send one at a time. You put one in, you wait till they mail you a letter back, it's acknowledged, you put the next one in the mail. Right? So obviously, that doesn't make sense. So there's an analogy for this in networking. What would you do in the Postal Service? You'd dump all the pieces in at once. I mean, if you really could only send one in an envelope, or maybe two or three, it's still going to take a bunch. So just dump them all in the mail at the same time. Maybe one of them won't make it, and you'll number the envelopes so you'll know which one, but you know, it'll work out. Probably that's not going to happen all the time. So on networking, the problem that we have here is if you have a network that's got high speed associated with it and is a long distance, your network manager, your boss, is going to be upset when they see it's very low utilization. So what happens is during this time here, let me turn off this. During this time window here, nothing is happening at the client. You're not introducing any more packets, but you could have been. The network puts bits in single file, one after the other. So you could have done something like, this. You could have sent a bunch of them at once. And maybe you know things about the network that I don't know, and maybe you tell me, look, we can do, but don't send more than 100 outstanding at a time. Let's wait until we get an acknowledgement back. Yeah, I know you've got time here to send like 1,000, but don't do that because you're going to get packets lost. You're going to regret it. So but don't send one either. So what this changes is the efficiency of the network. So in this case, they showed in their example that a cross-country network had a very low efficiency of 0.00027%, otherwise known as a CLM. Anybody know that? Career limiting move? Yeah, you don't want to run your network that way. Somebody will come and help you find something else to do for a living. So the question is, they asked, how large does the window size need to be? In other words, how many packets do I need to send at the same time simultaneously before I get an acknowledgement back so that I'm actually using 98% of the network's capacity? So what that means is in this area here, 98% of the time I'm busy sending packets, and only 2% of the time I'm not. So visually, the difference is obvious. Here I'm sending one, and so, 0.00027% of the time I'm busy actually transmitting this. The rest of the time it's dead. So what's it going to take for it to be 98%? Well, let's zoom in, way in on what this looks like. Here's what's happening. I start transmitting my bits here, and I stop transmitting. This is one packet, a single packet. It's this little line zoomed way in. So I'm going to spend some amount of time. It's very small, but it is not zero. And then the rest of the time, if you step off the time in this size and pretend that you were sending a second one, here when I'm doing nothing, I could have sent a second one. I would have used this amount of time to send the second one because it's how long it took to send the first one. And I could have sent a third one here, and a fourth one, and a fifth one. Meanwhile, this packet is making its way to the other side. At some point, the acknowledgement will come back. And when you were being super conservative, you waited until this happened before you started sending the next one. So the question is, how many of these can I send in order to make the time that I'm doing nothing as a ratio of the overall time only 2%? In other words, 98% efficiency. So the way we'll do it is figure out first, how big is this time? How long does it take to send one packet? Well, the book shows you and we'll have to pull it out, I think, to actually get it. So I'm going to go to the solution because I don't remember the number. But it had one here. Here we go. Okay, it takes 12 microseconds to send one packet. They told us that. All right, so 12 microseconds to send one packet. Let me move this up so we can still see it. All right, so 0.012 milliseconds for each of these blocks. What was the round trip time for the network? Well, traceroute can tell us that. We can look at the round trip time. And the round trip time in this case was 30 milliseconds round trip time. So from the time you drop a bit on the wire, it takes 30 milliseconds for it to get all the way there and back. And that's just propagation time. That's assuming there's no other kind of delay. You're just isolating that one variable. So 30 milliseconds for it to get there, plus it took 0.012 milliseconds to actually transmit the entire packet. So total time elapsed was 30 milliseconds plus 0.012 milliseconds. That's how long we worked from this point here. Here was the 0.012, and then we waited 30 milliseconds before the end of the acknowledgement showed up. Right, so if we want that to be 98% utilized, what we need to figure out is how many packets can we send in that time. So we want 0.012 times some number of packets in divided by the overall time from when we sent our first one to be 98%. Make sense? So we want to have lots and lots of these happen to make the numerator much, much larger so that the ratio is 0.98. So what's that number look like? Again, another great opportunity for me to embarrass myself. Divided by 0.12, 2,451 packets. So you're going to have to be willing to drop 2,451 envelopes in the mail and wait for your cousin to send you an iPhone screen snapshot of the puzzle all put together with no missing pieces. Are you willing to drop 2,500 envelopes in the mail and count on them all getting there? Probably not. So what would it take for the Postal Service to be 98% busy? Well, you would do the same thing. You would figure out how long does it take them to manage one letter, how much total time do they have, and you can do the math and figure out what it's going to take. Unfortunately, the Postal Service is built for peak season. They're built to handle Christmas. And the rest of the year, it's pretty much idle. Most systems are not designed that way. Routers are generally not really designed that way, which is why they have buffers. So if things do start showing up faster than they can handle, they'll just put them in memory and wait for it to drain. Hopefully, it'll slow down soon. When I worked at AT&T, we had always really interesting problems with florists. Florists have 12 weeks of the year when they're busy and need 100 phone lines. And the rest of the year, they need one. So Valentine's Day, Mother's Day, Christmas, Thanksgiving, and New Year's. That's when all the sales happen. The rest of the time, it trickles in, and they can get by with a single phone line. So how do you give someone 1,000 phone lines, 100 phone lines? And our tariffs were made, our rules were made that we charge you an enormous amount of money to install the phone and to disconnect the phone. And if you only kept it for a month, it was really expensive. So we made them miserable. And what it led to were things like FTD, where they just all pooled all those phones together and you call an 800 number and then they would hand them the order back again. That was at least more efficient. Now, nobody thinks about it twice. You just do it as a VoIP call or something. Right? They'll park all that stuff in the phone network. Okay, there's a diagram here on round trip times that I want us to take a peek at. Are we splitting each 8-bit number in half? No, and if you're talking about adding the checksum, you would actually split the packet up into a bunch of 16-bit numbers. So the implication is obviously every packet must be a perfect integer multiple of 16 bits, and it is. Right? So that's kind of the implication. But for our sake, for the homework, I didn't want us to add 16-bit numbers because I can't even write down 8-bit numbers, as you saw. So can you imagine what it would have been like if I'd done that in class? Okay, so here's a round trip time analysis, and I'll walk us through this one, but I'll decide at the end of class if it's going to be on if it's fair game for the exam or not. I don't think so. I'm leaning against doing this on the exam, so I want to kind of talk to you about what's going on. The idea behind this animation is to show you how the algorithm works in TCP that decides how long should I wait before I give up on a packet. You know, I sent you out to get lunch, and you've been gone for 30 minutes. Should I be nervous? Well, that depends, doesn't it? So if you sent me out to lunch and I didn't come back in 30 minutes, what would help you decide whether you should be nervous or not? How far away is the restaurant? How long is the wait? What's the queuing delay? What's the processing delay along the way? Maybe 30 minutes is perfectly fine. Maybe it's completely unacceptable because I asked you to go downstairs to the 7-Eleven and buy a sandwich, and you've been gone for 30 minutes. Like, what is going on? So this is the same issue that the network protocol has. You cannot hard code in a round trip time that is going to govern when you give up on a packet and decide it's never going to get there, I'm going to retransmit it. And the only thing you know is whether you've received an acknowledgement or not. There's lots of reasons why you may not receive an acknowledgement. Packet lost, packet dropped, router down, packet corrupted, packet received but system did not generate an acknowledgement for whatever reason, bug. Sent the ACK, but the ACK is taking a long time, the ACK got dropped, the ACK is corrupted. You won't know any of that stuff. All you know is, did I get an ACK or not? So the only thing you can do is write your driver, write your code to take action without having to know which of those things actually took place. So what will you do? What would you do if I don't come back and you give up and you're still hungry? What are you going to do? Send someone else, right? Retransmit. It's possible, isn't it, that I show up 5 seconds later with the food and a good explanation, in which case the transmission was needless. But this is exactly what happens in networking. So what this algorithm basically shows us is how we calculate it. And this was designed largely by one guy named Van Jacobson, who's still around 40 years later. In fact, he just helped Google rewrite a version of these calculations last summer, which was really cool to see after all these years. First, his stuff is working, and he's still kind of King Kong. So he's a very famous computer scientist and figured this stuff out long ago. So the idea is basically, and like I said, we're not going to do it on the exam, I don't think, but what you'll basically take is a sample of how long recent packets have been taking. You don't want to overreact. If you've been sending packets along and they've been taking 1 second each to get round trip, and then now suddenly one of them takes 2 seconds, you don't want to assume that the network has just permanently now decided to run at half speed forever and ever. No, it's just one packet. Don't overreact. You know, you drop all those envelopes in the mail, one of them takes 1 day longer than the rest. Don't conclude that the postal system's broken. Just average. Come up with some algorithm to do better than that. So what we'll do is we'll take 7/8 of whatever the value was before, plus 1/8 of whatever the latest sample is. So every time we send a packet, one of the things TCP does is it looks for packets coming back that it can use to recalculate the round trip time. And it varies. You can graph it. In fact, Wireshark will graph it for you. If you want to play around with it, you can get it to show you that. You'll have to narrow it down to a specific pair of IPs, but then it will collect data if you let it run, and it will show you a graph of what the round trip times actually are. So what you want to do is smooth that out. So you're going to take 7/8 of what it was before plus 1/8 of what it is now. So if the number is bigger, it'll raise your average. If the number is lower, it will drop your average, but it's not going to completely overreact because networks are like that. They do that. That's expected. And then we also are going to take a look at a value that looks at the absolute, at the standard deviation, basically, is what I'm trying to spit out here. So you're going to take 75% of what the value was before for the deviation plus 25% of what it is now, and what it is now is the difference between the old average and the new average that you just calculated. And so that'll get you a standard deviation number. That is now your new standard deviation. That is what goes into the next equation down here. You recalculate a new standard deviation. That is what goes into the next equation down here. Here is my current round trip time going into the problem. Here is the first packet after that. So here is my new estimated round trip plus the standard deviation, 4 times the standard deviation, in fact. So I take the average, 7/8 old plus 1/8 new, plus 4 times the standard deviation. Complicated, isn't it? And I get a new round trip time. I get a new timeout interval. For the next round, when I do it again, I'll just plug in whatever this calculation was, plus 1/8 times what the new estimate, and they told us the second packet took 340 milliseconds. Well, here it is right here, 340 milliseconds. I get a new estimated round trip time. I calculate a new standard deviation, 3/4 of what it was before up here, plus 1/4 of what it is now. And what it is now is the difference between the time now and the time it was before, and so forth. Right? So this will help you calculate that. So you can just pull up one of these, and we can try doing this. You also can really easily build an Excel spreadsheet. Here's what I'll warn you. There's a couple of bugs in this animation, and they're down at the bottom. And one of them, let me see if I can find them really quickly. You guys may see them before I do. And it's always possible he's fixed it because I've told him about it a few times. The author, by the way, is a really nice guy. And it's encouraging that I can actually call him. It's one of these numbers in here. They copied it down in the wrong place and did the math wrong. So forget the third one. Don't bother trying to use that. But you can use the rule for that. So anybody want to go through one? You want to try one? So the idea is basically my current value, let's see, is 210 milliseconds for estimated RTT, and the standard deviation number is 36 milliseconds. Okay, next packet shows up, 240 milliseconds. So I'm going to take 7/8 times my current average plus 1/8 times 240. And I'm going to get a new number. Somebody can calculate that and tell me what it is. For the RTT, I'm going to take 3/4 of what it was before, which is 36, plus 1/4 of the new deviation, which is 240 milliseconds for the new packet minus 210 for the previous average. And that's going to give me a new standard deviation. And therefore, my timeout, which is how long should I wait before I give up and send somebody else for lunch, is basically this value plus 4 times this value. All right, so help me fill in a few of these numbers. Louder? 213, that sounds right. 213.75. What about the standard deviation? Anybody get that? I don't have to watch. It's not a... 34.5. Is that what you get to? And therefore, the new round trip time is 13.75 plus 4 times 34.5. 351.75. That is my new timeout. For the next round, I will take this value as input and this value as input. I will not use this value as input. All right, so this will become this number. This will become this number next round, and continue on. So 5 minutes is my guess, is what that'll take for you to finish it. So what's the timeout value? When you send a packet, TCP starts a timer. That's the timer value. If you don't get an acknowledgement back by the time that timer goes off, or you don't otherwise see evidence that leads you to believe that the packet has disappeared, you will retransmit it when that time runs out, and you will start the timer again. Right? So that's how we basically deal with that whole long list of examples I gave you. Packet dropped, packet corrupted, packet misrouted, packets still coming, you're too impatient, it's slow, whatever it might be. All right? Okay. Make sense? It's not calculus. Okay? Could be worse. It could be raining. All right. Anybody know the movie that comes from? Anyone? Young Frankenstein. All right. The most important type of graph you need to leave this course understanding is one that looks like this diagram here. What this diagram is charting is how many packets I'm actually willing to send out at a time before getting an acknowledgement back. And we did the math a minute ago that showed for that one particular network, which is pretty fast, it's a gigabit network, we could reach 98% efficiency by sending 2,451 packets at a time before the first one's acknowledgement had a chance to come back. So we get a lot out there on the network. But is that smart? Is that the right thing to do? What TCP doesn't know is round trip time. So we just talked about how you're going to calculate how long you wait before you give up. But the other thing you need to know is how reliable is it? Like, okay, so it's going to take that long for a packet to get there, if it makes it. But there's car accidents, aren't there? I mean, there's two things you want to know about on the road. One of them is how long is it going to take, and am I going to make it, or am I going to have a wreck? They're independent, but related to each other. So what we want TCP to also pay attention to is not only be patient enough to let the packet get there, but don't overwhelm the network. Don't cause the traffic jam. Don't be the packet that filled up the router's buffer and caused it to start dropping things, because it's downhill from there. And you reach a saturation point. Interestingly enough, the stochastic modeling that you can use to predict traffic flows on the highways is exactly the same math that you use to predict traffic flows in networks. It's the same probabilistic distribution. It's the same stochastic modeling. We use exactly the same tools and textbooks. It's the same kind of stuff. It's traffic flow, independent elements. So here's what this is showing. When I first handshake with you, and now it's time for me to start sending data, TCP will try sending one packet to see if it makes it. If it gets an acknowledgement back, it will grow its window, which is what we call it, how big is the window, by another packet. So you should be listening to the recordings that are talking about this diagram by now. And if not, that's something you want to spend time on between now and the exam. Make sure you're caught up to at least that point. And it'll be the second week of lecture. It'll be exactly the same number of days into the lecture this semester as it was last summer, because this was on the midterm last summer as well, not this specific diagram. So I got an acknowledgement back. My confidence has grown a little bit. And so now I will send a window's worth of packets that's one bigger than it was before. I send 2 packets out. Each of them come back with an acknowledgement. Every acknowledgement that comes back, I add another packet to my window size. So the first of the 2 acknowledgements comes back, it's 3. The second of the 2 acknowledgements comes back, now I'm at 4. So I send 4 packets out in the next round. And I get 4 acknowledgements back. They make my window size grow from 4 to 5, 6, 7, 8. Right? Do you see how I'm growing exponentially? 1, 2, 4, 8. If I send 8 out and I get 8 acknowledgements back, I'm going to be at 16. If I send 16 packets out and I get 16 acknowledgements back, every acknowledgement is going to make me grow my window by 1. And I will end up at 32. So this is how TCP starts off. It grows exponentially, and hopefully all the packets make it. If at any point one of the packets doesn't make it, it starts over, basically, because it's assumed to be lost. It could be any of those reasons. However, we're smarter than that. We don't just want to grow exponentially. We have some help from the operating system. The operating system will suggest to us a value where we should knock it off, slow down. You're getting close to what I think is the capacity of the network. So tread carefully. Inch your way forward from here. And that is called a slow start threshold. And we haven't had a chance to go over a bunch of this because it's in the recordings, but it's really critical that you listen to them, because we will not go over it in detail in class while I'm standing in front of you, okay? So you'll learn that this area, while you're growing exponentially, is called a slow start area. And I'm going to go ahead and show you the labels down here. So this is slow start. Start off at 1, and we grow exponentially until we reach a value. And the way the animation is written for our textbook, there's lots of variation in the way this gets written, so it's important to point out what's going on here. At the beginning of a transmission round, let's say I'm at, somehow or another, I'm at 7. Okay, I'm at 7. And this little red plus dotted line that you see here is my threshold when I should stop growing exponentially. And it starts off, I happen to be able to see this at the value of 8. So the question is, what should I do when I get to 8? You should stop growing exponentially. Okay, I'm at 7 now. I'm ready to send 7 packets. Should I send all 7 or should I just send 1? The way this animation does is it says checks 1 time at the beginning of the transmission round. If I have not met the threshold, continue on. So I will blast right past that value and go to 14 if I were really at 7. In this case, they made it a little neater. I happened to finish a transmission round and was lined up perfectly with the threshold. Well, that makes it easy. So here I am, ready to start my 4th round of transmission. The first one I sent 1 packet, then 2, then 4, then 8. And I check the value of the threshold. I've reached the value, it's 8. So I do not want to grow exponentially anymore. So I will send 8 packets out in this window, and when I get all 8 of them back, I will be at 9. I send 9 out, I get 9 back, I'm at 10. I send 10 out, I get 10 back, I'm at 11, 12, 13, 14, I'm growing linearly. This area where you grow linearly, and you can see it right in front of your face, it's obvious when you look at the graph. This has a name as well, and it's called congestion avoidance. Well, that makes sense. So if you can't remember which one's slow start, just try to figure out which one's congestion avoidance. Okay, that's got to be that one. I'm being careful, I'm growing linearly, I'm trying not to overwhelm the network. If you grow exponentially, you're far more likely to overwhelm the network. So you don't want to do that. And you will continue on this way forever and ever and ever until you detect a loss. Now, you'll notice I'm very careful not to say until there's a loss, because you don't really ever know. All you know is that you didn't get an acknowledgement back for something that you expected, and your timer went off. So you detect a loss, but you don't really know. Fortunately, you also don't really care, because you're going to do the same thing in either case. You're going to retransmit the packet. Okay, so what TCP showed in this example, and the lectures kind of build up through this. So if you're having a hard time kind of holding on to this, definitely you'll need the lecture to kind of go into a lot more detail for you guys. What happened in this case was different than what happened in this case. And you can see that visually. I grew exponentially, and then I grew linearly, and there was a loss. I can see it says there was a loss, but I also can view that something different here happened. I slowed down. I shrunk the number of packets that I was willing to send in my window at a time from 20 to 13. And then I started growing again. And here I was at 19, and I had a different kind of loss, and I dropped this time all the way back down to 1. So what's the difference between these two? Why sometimes would I drop all the way to 1, and sometimes I would drop only to something a little more than half of that? Well, the reason is that there are other hints that a packet is missing. So for example, if I send you 10 letters separated a day apart, on day 1 I send you a letter, on day 2 I send you letter number 2. For 10 days I do this. And I ask you, when you receive the letter, please send me an envelope back acknowledging it. Thank you for the gift. 12 days of Christmas, whatever you want to make it. So I get back a few days later a letter saying thank you for envelope 1. I'm looking now for envelope number 2. The next day I get a letter that says thank you for envelope 2. Okay, so I'm already setting up a pace. I now can figure out how long it takes the letter to get there and for yours to get back, because now I've started getting your letters. And I get envelope number 2, and it says, thank you, I got 2, now I'm waiting for envelope number 3. Of course, this has all happened in the past now, because it took time for the letter to get there. But when he received envelope 2, he wrote you a thank you note and said, I'm looking forward to getting envelope 3 tomorrow. I can't wait, and drops it in the mail. So you get the acknowledgement back. You find out later. So what do we know at this point? Do we know whether he's gotten anything past envelope 2? No. Hopefully he has, but until we get the acknowledgement, we don't really know what's going on. Here's what's going on. Envelope 3 got shredded by some malfunctioning postal machine, and it's never going to make it. So he goes a day without an envelope. The next day, envelope 4 shows up, because you've sent these things in the mail. Envelope, excuse me, envelope 4 shows up. What would you do if you got the wrong envelope? Well, what TCP does is it will write you a note saying, listen, thank you very much. I did get an envelope, but it wasn't the one I was hoping for. I was really hoping for envelope 3. Would you mind, sending me envelope 3? And that'll eventually make its way back to you. In the meantime, envelope 5 and 6 have also arrived, and he's like I said, thank you very much for this envelope, but I was really looking for number 3. So you're the sender. Let's review what's happening. You send 10 envelopes out. You get an acknowledgement back for 1, and the acknowledgement from 1 says, thank you for the envelope, I'm waiting for 2. Then you get one that says, thank you for that envelope, I'm waiting for 3. And then you get another one that says, I'm waiting for 3. And another one that says, I'm waiting for 3. And another one that says, I'm waiting for 3. What are you going to figure out pretty quick? Send 3. Right? You don't need to wait for the timer to go off. You also know that the Postal Service is working pretty well because obviously more envelopes are arriving because you keep getting more acknowledgments back. It's just that the acknowledgement number you're getting back is telling you that something's missing. Maybe it'll sort itself out if you wait a little bit, but here's what TCP says. If you start getting repeats back where people are saying thank you for that, but I was really hoping for number such and such, if you get 3 of those in a row, then wake up. It's probably never going to make it. I mean, obviously, 3 packets after it made it, so where would it have gone? Why would it be like 3 packets later? It took a detour, like sending me out for lunch or something. So your code, the latest versions of TCP, which is what the book focuses on, is called TCP Reno, and it, in the book, the lectures will tell you why it's called that. They kind of added that as an after the fact. So here's what worked for the first so many years. You would get to a point where you detected a loss, you would start completely back over. You would reset the value of your threshold to 1/2 of what it was before. So it was 8. I had a loss at 20. My new threshold value is 10. So I set it to 1/2 of what it was before. And the lecture will tell you a little bit about this. For the exam, all I expect you guys to be able to do is label the parts of the diagram. I don't have enough confidence that going through the recordings is working well enough for you that you'll be able to answer all the detailed questions, and we will end up going over a little bit more of it after the test. So for now, I want you to have a feel for it. You do need to listen to the lecture recordings on it to kind of build up your knowledge on it, but I want you to be able to point out the various parts of the diagram, know what congestion avoidance is, know which parts of the diagram demonstrates that you're in slow start mode. Where are the thresholds? Where are their losses? So you think you can do it? Let's try a couple. Is he going to do it? Here we go. Let's do a couple together. All right. Threshold. It's always a horizontal line. I mean, that part's easy. And I can see that I change behavior when I reach it as well. So below the threshold, I'm in slow start mode. So I'm in slow start mode here, 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 and here. So this one would be between transmission rounds 1 and 4. And this would be between 24 and, I reach the threshold here. That looks like a 28 to me. And also 31 through 35. And then one last one, 39 through 40. These times I was in congestion avoidance, and you can figure out what those numbers are. And losses occurred, and I don't care what you say, losses occurred at round 16 or 17, just so I know you're looking at the right part of the graph. Another loss here, another loss here, and another loss here. All right, let's do another one. Okay, this one is a little bit more gnarly. So let's paste it in. Where's slow start on this one? We start off always in slow start. 1 until when? Looks like about round 4, like right here, right? And you can see a little red plus. It's impossible to see, I know, but it's there. That's a threshold. Okay, are there any other places on this diagram where we're in slow start? You know, round 18 here, looks like. Anytime you go back down to 1, usually you are. This one doesn't look, you know, linear, but it's hard to tell because when you're growing linear from 1, you go 1, 2, 3, 4. If you're growing exponentially from 1, it's 1, 2, 4, 8. You can't tell by seeing 1, 2 which one it is. So I will not give you one that's tricky like that. All right, it's just a random one that the website generated. But it looks like it stopped maybe here. Same thing with this one, and that's it. Where am I in congestion avoidance? Everywhere else. Where are there losses on this diagram? Anytime you slow down, it's because you detected a loss. So here, right? Here, 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 and even here. I didn't do my normal growth. So if you step back and looked at this and said, is this network working very well? I would say no, but you are getting packets across. But it looks very congested to me because sometimes you're able to send 18, 19 packets at once and get all the acknowledgments back. And sometimes you're only able to send 2 at once and one of them's lost and you have to start over. So it's wildly variable. I would not want to be on this network. But it's great for building examples. So what this URL will do, oh God, that one's really bad. What this URL will do is for every one of these that it draws, you can say show solution, and then you can scroll on down, and it'll label the areas for you. So I'll want you to do more on the homework than on the test for this. What the homework is basically asking you to do is, and it goes through some detail, let's copy this over and see if we can answer this. Is he going to do it? I'll have to probably do it this way as a screen snapshot. Yeah, it may not cooperate. So I am copying it. I can see it get copied. And oh, I'm copying the wrong. I'm pasting in the wrong application. Duh. All right. Okay. So what am I being asked in the homework problem? The first thing I'm asked is, what are the time ranges where slow start begins? So what do you think? 1 through 4. Is there another one? 31 through 34. You agree? All right. Now list the time ranges where it's in congestion avoidance. You can say all the other times, and I'll take it. But if you want to write them out, it's 5 through 20, 21 through 22, 23 through 28, 29 through 30, 34 through 35, and 36 through 40. That's a lot. Just say all the rest if you want. All right. When is it in fast recovery? So fast recovery is when you don't go all the way down to 1. So there's 1 here, 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 and here. And I see 1 all the way over here. On the test, you can circle them if you want like that and just write FR next to it or something like that. So you might want to bring a couple of colors of pens or something like that if you like drawing the stuff out. I'll take it any way you give it. You can write it on the side, you can circle it, you can draw arrows, doesn't make any difference to me. I just want to see that you know largely how to do it. Okay, give the transmission round number and where the losses are. So the first loss occurs here. We can see it visually. Things go down. If it goes down to 1, it's a timeout. You never got a hint. If it doesn't go down to 1, it's that situation where you kept getting more envelopes and you finally figured out, okay, it's never going to make it. I get it. I don't need to wait for the timeout. I'm going to go ahead and resend envelope 3. Right, so those are triple duplicate acts, and the lectures go into it in more detail. So at time 4, there's a loss, and it's a 3DA, triple duplicate act. You can write it as literally the letters triple duplicate act if you want. That's fine. There's one here. In fact, the only timeout loss in the whole diagram is right here. All the rest of them are triple duplicate acts. So there's a loss at 4, at 20, at 21, at maybe 22, and at 28, and 30, and 35. It would have killed them to put the numbers under the lines, wouldn't it? So there's a handful of them in there. Okay, and then when does the threshold value change? We will not have that on the exam, but I will just tell you that it changes at every time there's a loss. You do not need to worry about the values for the homework. Right, so I will. Are you guys like editing the homework file right now, or are you taking notes? Okay, so just delete this part, and I'm going to resave and overwrite it on the shared drive because I don't expect you guys to answer that one right now. I did go ahead and put the diagram in on this one for you to help you. So it's in there. It's important that you understand the green from the yellow and where there are losses. So this is what TCP is doing all the time. When you turn on your computer and you give it a 5 gig movie file to transmit, it's going to do it packet at a time, and it's going to start by sending 1 packet. After the handshake, it will start by sending 1 of your million packets. And then if that goes okay, it will send 2 more of your million packets, packets 2 and 3. And then it'll send 4 more, packets 4, 5, 6, 7. And you know, it's going to continue whittling away at this until the file's sent, until the whole thing is done. So without ever knowing how many routers, or the speed of the network, or how many hops there are, or what the congestion level is like, how far away the other end is, it's able to prevent congestion and from overwhelming the recipient without ever knowing anything about the other end. Blind. So you can send packets to someplace you've never sent before that take a route that your router has never sent things to, and it'll still make it. The algorithm will detect when there's congestion. And one of the ways, one of the biggest problems, one of the most dangerous types of congestion is when it's because a router's buffer has gotten full and it's just starting to throw away packets. So that's why we back off. We don't know if that's the type of loss that occurred or if it's any of those other 20 things I mentioned. But we assume it's the worst one, and so we slow down. We don't want to overdo it. Okay? All right. Then the last one that we've got for this is another animation. And this isn't exactly TCP, but it's pretty close. And what this shows is I have a window here that's size 5. And you can see the rectangle around the sender. The sender's at the top, the receiver's at the bottom. I can send a packet. It will make its way to the other side. The other side sees it. It says that, in fact, was the number I was expecting. I was expecting packet 0, so I'm going to send you back a thank you note. And when you get the thank you note, you're like, awesome, sent and acknowledged. We can both forget about 0. So he removes it from his buffer. He doesn't need to keep a copy of it around anymore in case it got lost, because he doesn't need to retransmit it because you told him you got it. I can send 2 more packets. What this animation doesn't show is that your window size would have just grown from this. It doesn't show that. So I got both of those. The acknowledgments are making their way back. When I get the acknowledgments, I'm happy. So you notice the receiver moves along before the sender does. The receiver has the easy job. The receiver receives packets and sends acknowledgments and forgets about it. The sender has to stockpile all packets outstanding until they're acknowledged one by one. And if one of them is not acknowledged, then it will have to resend it. So I'm going to kill off this packet. 3 is never going to make it. And I'm going to resume. 4 and 5 will make it. He'll go, okay, I can't give them to the application yet because what you asked me to do when you implemented me was to create this illusion that the two applications were talking directly to each other. So if the application thought it was important to hand me the packets in a certain order, I'm going to make extra careful to give them to the application at the other end in the same order. And what you just did is you gave me 2 packets, thank you, but they were not the ones I expected. So I'll hold on to them for now, hoping you send me missing packet 3. But in the meantime, I'm not going to give them to the application because he got packet 2, but the next one he's expecting is packet 3. That makes sense, right? So I'm going to get the acknowledgement. What do you think is going to happen at the sender? This is that situation where you get an acknowledgement back out of order. This is not the one you set. Well, one thing you're not going to do is move your window, because when you move your window, you basically are saying, I'm forgetting about you forever. He can't move his window past 3 until he gets an acknowledgement for 3. He's running a timer right now. You can see it happen at the bottom. Timer started for packet 3, 4, 5, and at some point here, and I have it running kind of slow, at some point here, it'll resend it. There it goes. Timeout occurred for packet 3, resent packet 3, timer restarted. Now, packet 3 arrived. Did you see what happened to the window? Now 3 arrived. Now he's got 3 packets, the one that just arrived and the 2 that he was holding on to that he can now give to the application. So he slides over 3 at once, and he acknowledges the one that was missing. What's the sender going to do when he gets the acknowledgement for 3? Yeah, he'll slide his window to the right as well by 3. Bam. So if I speed this up a little bit, let's reset it. I'm going to just keep hitting the send button. Nothing's happening until I have more room in my window. When I have more room in my window, more stuff gets sent. Do you see that? I keep hitting the send button, and I'm sorry about the microphone. I know you can hear it. So what do you notice happening here? It takes no time to transmit the packet. All the waiting time is propagation delay for it to get there and for the acknowledgement to come back. So we don't try to send TCP packets in bursts, 10 packets at a time, and then 11 packets at a time, and then 20 packets at a time. It's just the way the math works, because propagation delay is much larger than transmission time. I can hit send all day long, but until a round trip has occurred, there's no opportunity for me to send more until my window slides over. Once there's blank space in my window, then I can send more packets. So if you graph what this looks like, it looks like this. If I smooth it out a little bit and make it look a little prettier, here we go, that one I don't have. What you'll see is what is known as sawtooth behavior. You'll grow your window, shrink on a loss, you'll grow, you'll shrink on a loss, you'll grow, you'll shrink on a loss, you'll grow. And this is maximum capacity, and this is 1/2, because we drop it by half when there's a triple duplicate ACK. What's the average value for this? Well, you can see it with your own eye. The average is right down the middle, 3/4. So TCP gives each user 3/4 of the capacity, max capacity they can use. So what this implements is fairness. So I'm going to add one more thing. TCP also doesn't know with how many other users it's sharing any given segment along the way. How could it? 5 hops down the network, there may be 1,000 users sharing that next link, none of whom have anything to do with your part of the world. It may be all from South America. And 5 hops away, it's a router in France. So you're taking one route to get to France, Brazil, and everybody else is taking another route to get there. And, oh, sorry, she was calling me. And you may not know. So how do you make sure it's fair? How do you not use more than your fair share of the network? This guarantees that as well. So what will happen is it will balance out and every user will get their fair share of the network, which is quite incredible. If I told you to write an equation that would do that, and you can't know how many links, you can't know how many users, you can't know how much bandwidth, you can't know how many hops, you can't know how big the buffers are, go ahead and write your algorithm now. I'm not going to give you any variables at all. The only thing I'm going to tell you is you can look at the timestamps and figure out how long it takes something to come back, and you can conclude if you don't get an acknowledgement. But that's it. I'm not going to tell you anything else. We're going to build a worldwide network with a few billion devices on it that's got to work all the time. Sounds easy, right? So that's why this guy is famous, Van Jacobson. He had the right kind of modeling background to do that stuff. You should look him up. It's an interesting Wikipedia page. Okay, so if we've got this here, packets 0 through 4 are sent. The second packet is lost. What will the sender do? Yeah, you can send a snapshot, and the snapshot you want to use is one that basically shows you send 5 packets, pause it, pick packet 2, or you can assume that by packet 2 I meant this one, I don't care, and let it run. And so the question is, what will the sender do? So what will he do? He will wait and retransmit packet 2. He still has packet 2 in his buffer, so he can retransmit it. You don't go back to the app and ask for it again. You hold on to a copy of it, just in case you need it. Okay, 5 packets are sent. Acknowledgement number 2 is lost. All right, that's a little different. Let's do that one. 1, 2, 3, 4, 5. We'll let him get there. We'll have him come on the way back. I'm going to stop and kill off acknowledgement 2 and resume. What's the sender going to do? Yeah, so is there any difference? Does the sender do anything different, though? The receiver does, but does the sender? No. Why? Exactly. He has no way of knowing what's happening on the network. He doesn't know whether the packet got lost or the ACK got lost or what's going on. So how can you have him do different things based on that knowledge when you can't ever have that knowledge? Why didn't the third envelope make it in the mail? Who knows? Maybe it'll show up eventually. I don't want to wait that long. I'm going to resend it again. Right? It's practical. It's exactly what you would do without knowing what's going on the inside. Okay, will the sender do anything different? No. Why or why not? Just what he said. It doesn't know. You can't know what's going on. Will the receiver end in a different state? Yeah, very much so. The receiver will look different. In the first case, he slid, only over to 2. He never got packet 2. In the second case, he got all 5 of them. So the acknowledgement was lost, but that's not on him. He doesn't care about that. The receiver got him, sent the acknowledgement. If the sender wants to do something about it, he will. So what will happen is the sender will resend 2, and the receiver will go, yeah, thanks, I already have it. Thanks, but thanks. Here you go. I'll acknowledge it. You must not have gotten my acknowledgement, I guess. So he'll resend it. Okay, at the end, when they reach their steady state, is there a difference between the 2 scenarios? In other words, if I just let this run and let the timeout or whatever's going to happen. Remember, this is the example where the ACK was lost, right? All right. Nothing more is going to happen. Agreed? Until I send more packets. Does this look any different than the final state when the packet was lost? No. You better hope not. Do you want the success of your file transmission over the internet to depend on whether it was the packet that was lost or the acknowledgement that was lost? Why would you want to know that? Right? You want TCP to deal with it either way, and send the file. At the end, you want your file sent. So the end state, no matter what really is going on, has to be the same. So you have to write your code to recover and deal with these losses out of order, duplicate acts, acts misnumbered, acts correct, all that stuff, and recover from it. Okay, so for the exam, I will ask you a few more questions like this for TCP and UDP. I will give you another scenario, short scenario, with some multiple choice on it. I will ask you to do a ones complement for me. So practice that. I will ask you to calculate efficiency and spot the areas on this chart. That's it for that homework. Let's go look and pick one or two out for the other ones. And here's summer 19. Open up. Okay. I will give you a picture of one of these scenarios from the animation. And I will ask you to tell me, does it demonstrate persistent or non-persistent? And is there parallelism? And I'll have to tell you how many packets are being sent before you can tell. If I tell you there's 10 packets sent and you see 10 individually, obviously nothing is happening in parallel. If I tell you there's 10 packets sent and you see one thing being sent, then obviously there's a lot of parallelism going on. So there's only 4 or so combinations. Play with the animation. If you did the homework, you're prepared. You don't need to do anything more for it. You're all set on that one. I will give you, if I can come up with something super simple, I'm not going to have you do the math on this. What I'll probably ask you is, show me the formula. How many delays, how many links, how many routers, how many times you're going to need this, or I'll give you the values and just ask you to tell me what the total is. So as long as you kind of work through this problem, you're completely prepared. You're totally set for that one. Okay. I will not ask you another DNS question. I will ask you one on P2P versus that. You can bring a cheat sheet. So what I would bring are the formulas. And I had them in the recording. Do you remember them? Remember when I pulled it up and I showed you the diagram? It might help if I sent that to you guys for you to include. And at this point, I might even actually put them on the exam to show you the formulas. But I'll give you a scenario. I'm not going to have 9 computers. It'll be like 2 or 3 or 4, something like that. And I'll give you values, and I'm going to ask you, all right, which one's faster, client server or peer-to-peer? And you'll have to show me how to, which one it is. So go back to last Wednesday's recording where we went over this. I pulled up the formulas in a little table for you. I'll try to pull those this afternoon, but that's what I'm hoping you'll have. All right, that's it. Okay, and then from 2, I'll run out of energy to give you anything else quickly. Okay, I may show you a trace route and ask you a couple of questions about it. Make sure you look at this example in the trace route where I have multiple lines for the same hop. And I need to open this up actually because it's hard to read, I know. Okay. No, I can't do it in that one. Shoot. Okay, let's try here. We can at least get it on the recording that way. Homework solutions 1 and 2 are up, but not 3 and 4 will be up tonight. Okay. Here we go. I will show you a trace route. It's like scrolling crazy on me. So remember, when you see more than one answer for a certain hop, it's because the answers are coming from more than one router. And why would you do that if there's too much for one router to handle? You can hand packets out and divide them up as they come in. There are devices that will hand parse them out to multiple routers. That's what happened in step 8 here. My first packet went to 62.214, the next one went to Versatel, the next one went to 62.214, the same router again. So those are the 3 hops in that case. All right. And then homework 1. Let's take a quick peek at it. I may not ask anything on it if it won't, especially if it won't open the file for me. This is where you hope my computer doesn't work. Okay. Golly. I don't know if it's going to show me. Let's try this way. I'll give you a problem on, here's a file size, here's my transmission speed of my network, and the length of the network and the propagation speed. Tell me how long it's going to take. 5 megabyte file sent on a 100 megabit per second network for 100 kilometers at 2.5 times 10 to the 8. It'll always be 2.5 times 10 to the 8 meters per second. How long is it going to take? And I'll give you probably multiple choice on it, so you'll be able to grab it. Make sense? So when I write it, probably 1 or 2 of these problems we talked about, I'll throw out because I'll get cold feet, or I'll realize, like, I don't think we can do it in time. I think it's going to take too long, and I'll throw it out. So don't study your guts out on the one problem you're scared to death you don't know, because it's guarantees you'll walk in and I will have removed it from the test. And you'll be like, why did I spend all my time on something that's not even on the freaking exam? So make sure you spread your time out and increase your odds. There's not going to be one killer problem that'll flunk you on the test. The harder problems will not be worth tons more points. They'll be balanced, okay? The test is in person here on Wednesday, and my target is for it to take an hour, not 2 hours, and you guys can bail after that. All right, sound all right? Okay. Last time I did this, some people finished in 15 minutes. So it's like, okay, well, you studied, obviously. So it's, I don't know if that's always doable, but there's always one, isn't there? There's one in every class. Do you guys know who that'll be yet? Have you figured out that person yet? No, taking pools? I have a couple of ideas. So anyway, all right, thank you guys very much. I'm sorry I kept you all the way to the bitter end. Could you post this? Yeah, as soon as it's over. They killed me last week. They had some problem with their recording stuff, and it took 2 days. But I'll make sure this one. I'll keep an eye on it, a hard eye on it. Yes, it'll be right here where we are now. Right. Bye, guys. See you all.